Dear students, do you want to get into the fascinating world of physics? Please see this video and also subscribe to this channel. Dear students, in this video we are going to study about the phase difference and path difference between the waves of light sources. What are coherent sources and double slit as coherent sources?
Let's jump right in. Welcome to the Explainer. Today, we're exploring one of the most fascinating corners of physics, wave optics. We're going to visualize how light travels, not just as simple, boring straight rays, but as intricate, overlapping waves. And more importantly, we'll see exactly what happens when these waves crash into each other. If you've ever wondered how light truly behaves on a fundamental level, you are absolutely in the right place.
Now, I want to start with a question that honestly sounds a bit like a riddle. Can adding two light waves together actually create total darkness? I mean, common sense tells us that turning on a second flashlight in a room just makes it brighter, right? Definitely not darker. But in the strange and beautiful world of wave optics, light plus light can literally equal absolute darkness. Okay, let's dive into this counterintuitive paradox and uncover the precise mathematics that makes it happen.
To understand how light can actually cancel itself out, we first have to picture how it moves. Think of dropping a stone into a perfectly still pond. You know those expanding circular ripples you get? Well, that is exactly how light waves propagate. In physics, we call each of those ripples a wave front. And a wave front is simply the locus of all points that are in the exact same state, or phase, of vibration. Just like water molecules move up and down together to form a crest, light waves have their own invisible crests and troughs traveling through space.
So what happens when two of those ripples crash into one another? We get a phenomenon called superposition, which leads us to the formal definition of the interference of light. It's defined as the phenomenon of the superposition, or overlapping, of two light waves, which produces an increase in intensity at some points and a decrease in intensity at others. But here's the thing, it's not just a chaotic collision, it is a highly predictable, strict mathematical addition of wave energies.
Let's break this collision down into two distinct outcomes. Over on the left, we have constructive interference. This is when the crest of one wave perfectly aligns with the crest of another. They team up, producing a much larger amplitude, which gives us a bright region. But look over on the right at destructive interference. This right here is the answer to our paradox. If the crest of one wave perfectly aligns with the trough of another, their energies effectively cancel each other out. The displacement is zero, and the result? Total absolute darkness.
So, how do we predict whether two waves will team up to create a bright spot or completely cancel out to create a dark spot? To solve this mystery, we need to introduce our two mathematical detectives that govern all wave behavior: phase difference and path difference. These two concepts are deeply interconnected, and they are literally the key to understanding wave optics. Let's start with the first detective, phase difference, represented by the Greek letter phi. Phase is the angular position of vibration as a wave progresses. If you picture a wave as a continuous cycle, one full wavelength corresponds to a phase of 2 pi radians. So the phase difference is simply the angle between two superposing waves. Are their cycles perfectly synced up, or is one lagging slightly behind the other? As we're going to see, this phase difference is directly determined by the physical path the wave takes. That brings us to our second detective, path difference, represented by the symbol delta. While phase difference is about the angle of the wave cycle, path difference is about literal physical distance. The crucial point is this: if two waves travel from sources S1 and S2 to an observation point P on a screen, the path difference is simply the physical distance of S2P minus S1P. And here is the beautiful mathematical link between our two detectives. Phase difference equals 2 pi divided by the wavelength multiplied by this path difference.
And this brilliantly illustrates exactly how these mathematical rules play out in reality. Check out the constructive interference row. If the path difference is a whole number multiple of the wavelength, written as n times lambda, the phase difference is an even multiple of pi, and boom, we get a bright fringe. But look at the destructive row. If the path difference is an odd half wavelength, written as 2n minus 1 times lambda over 2, they arrive totally out of phase. Crest meets trough, and we get a dark fringe.
Okay, so the math is solid. But that brings us to a very practical, real-world question. If light plus light can create dark spots through destructive interference, why don't we see dark, zebra-striped shadows flying across the room when we turn on two separate light bulbs in our living room? I mean, the math says it should happen, so why doesn't it?
The answer lies in the strict environmental conditions required for interference to happen, specifically something called coherent sources.
You see, two normal light bulbs are completely independent. Because of random thermal vibrations inside the bulbs, their atoms emit light waves with rapidly changing phases. They're what we call incoherent. For us to actually observe a stable interference pattern of light and dark, the two overlapping waves must come from coherent sources, meaning sources that maintain a constant phase relationship over time.
Now, it is incredibly difficult to get two separate sources to be coherent. Here is the strict textbook checklist. First, the sources must emit the same frequency or wavelength, meaning they need to be monochromatic, just a single color. Second, they must have a constant phase difference, or be in the exact same phase. Third, they must have the same waveform. And finally, preferably, they should have the same amplitude to ensure those dark spots are truly completely dark. Without these conditions met, the interference pattern shifts so incredibly fast that our eyes just see a blur of average, uniform brightness.
Because two independent light bulbs can practically never be coherent, physicists had to get a little clever. They developed three main techniques to trick a single light source into acting like two perfectly matched, coherent sources. The first is wavefront division, where a single wave is physically split by passing it through tiny slits. The second is intensity or amplitude division, which uses partially silvered mirrors to split a beam, like what you'd see in Michelson's interferometer. And the third technique uses a source and its own virtual reflections, which is used in tools like Fresnel's biprism or Lloyd's mirror.
Out of all these techniques, the absolute most famous and historically significant is the one based on wavefront division. I'm talking about Thomas Young's double-slit experiment performed way back in 1801. This right here is the ultimate proof of the wave nature of light. By brilliantly designing a setup that forced light to interfere with itself, Young proved beyond a shadow of a doubt that light behaves as a wave. And he did this long before we had lasers or modern optics.
Let's move to the actual laboratory setup and see how this builds together. First, Young used a single monochromatic light source to emit a uniform wavefront. Then, he placed an opaque screen in front of it with two incredibly tiny, closely spaced slits, which we label S1 and S2. Now, because these two slits are exactly equidistant from the original source, they catch the exact same wavefront at the exact same time. Suddenly, S1 and S2 act as two perfectly identical, mathematically coherent sources. The waves emerge from the slits, spread out, overlap, and hit a viewing screen about a meter away.
And what appears on that screen perfectly validates everything we've just talked about. At the exact center point on the screen, waves from S1 and S2 travel the exact same distance. So the path difference is zero. Therefore, they arrive perfectly in phase, giving us a vibrant central bright fringe. But as you look off-center, those distances change. One wave has to travel further than the other. When the path difference hits half a wavelength, boom, a dark fringe. When it hits a full wavelength, another bright fringe. The result is this beautiful, perfectly spaced pattern of alternating bright and dark bands, dictated entirely by the math of path difference.
It is truly remarkable to think that something as fundamental as light can be mathematically engineered to cancel itself out into total darkness. But look, this isn't just 19th century laboratory trivia. Now that you know the precise conditions required for coherence and interference, ask yourself, how might these exact same wave optics principles be secretly powering the lasers, the fiber optics, and the data transmission technologies that run your world every single day? The math of the double slit isn't just in the textbook, it is literally the invisible architecture of the modern age. Thanks so much for joining me on this explainer, and keep questioning what you see.
Now let us study about the phase difference and path difference between the waves. What is phase? It is the angular position of vibration, and when a wave is progressing, there is a relation between the phase of the vibration and the path traveled by the wave. We can express the phase in terms of path difference and vice versa. The path of a wave, one wavelength lambda, corresponds to a phase difference of 2 pi, as shown here. So a difference of path difference of lambda will give rise to a phase difference of 2 pi. A path difference delta corresponds to a phase difference phi, as given by the equation delta equal to lambda by 2 pi into phi, or phi equal to 2 pi by lambda into delta. And for constructive interference, the phase difference should be satisfying this condition, as phi equal to 0, 2 pi, 4 pi, etc. Hence the path difference must be delta equal to 0, lambda, 2 lambda, etc. So in general, it is the integral multiples of lambda. That is, the path difference should be written in terms of integral multiples of lambda, like this. That is delta equal to n lambda, where n is equal to 0, 1, 2, 3, etc. in integers. And for destructive interference, the phase difference should be pi equal to pi, 3 pi, 5 pi, etc. Hence the path difference must be written as delta equal to lambda by 2, 3 lambda by 2, etc. That means half integrals of lambda. So the path difference delta is given by 2n minus 1 lambda by 2, where n is equal to 1, 2, 3, etc. Now let us study about the coherent sources. How we can say that two sources are coherent. The two light sources are said to be coherent if they produce waves which have same phase or constant phase difference, same frequency or wavelength, monochromatic, and same waveform, and preferably same amplitude. Now let us see what is coherence. So here this coherence means it is the property of waves that enables to obtain stationary interference pattern. And two independent monochromatic sources can never be coherent because they may emit waves of same frequency and same amplitude but not with same phase. So this is because atoms, while emitting light, produce change in phase due to thermal vibrations. Hence these two sources are said to be incoherent sources. And how we can get coherent sources? For that we can have these following techniques. First one is called wavefront division, that is like this. The wavefront will be divided into two. And the second one is intensity or amplitude division. And third one is source and images. Now let us take the first condition, that is wavefront division, which is the most commonly used method for producing coherent sources. And we know that a point source produces spherical wavefronts. All the points on the wavefront are at the same phase. If two points are chosen on the wavefront by using a double slit, the 2 points will act as coherent sources, like this S1 and S2. Then the second one is intensity or amplitude division. If we allow light to pass through a partially silvered mirror, like this is a partially silvered mirror. That is called as a beam splitter. Both reflection and refraction take place simultaneously, and as the two light beams are obtained from the same light source, the two divided light beams will be coherent in nature. They will be either in phase or at constant phase difference, as shown, and instruments like Michelson's interferometer and Fabry-Perot Echelon work on this principle. So this is the splitting of coherent light into two sources. And in the third one, the source and images. So in this method, a source and its image will act as a set of coherent sources, because the source and its image will have waves in phase or constant phase difference, as shown. The instrument called Fresnel's biprism uses two virtual images of a source as two coherent sources, and the instrument called Lloyd's mirror uses a source and its one virtual image as two coherent sources. So like this. This is in case of Fresnel's biprism, there are two prisms which are used to produce two virtual images like this using a single source. Whereas in the case of Lloyd's mirror, one source will be real one and the other one will be virtual. Now let us study about double slit as coherent sources. Here in this case the double slit uses the principle of wavefront division, and there are two slits S1 and S2 which are illuminated by a single monochromatic source S, which act as two coherent sources. These two slits S1 and S2 will act as two coherent sources, and here the waves from them travel in the same medium and superpose with each other. The constructive and destructive interference formed by them are shown here in 7.11 here. And the crests of the waves are shown by thick continuous lines, and troughs are shown by broken lines. That is in the figure 7.11b. Like this. And The points where the crest of one wave meets the trough of the other wave, we will have the waves which are out of phase with each other, and in that case the displacement is minimum and these points appear dark, and that's called destructive interference. Now, how do we get bright fringes? For that we have this constructive interference, and in this case we have the points where the crest of one wave meets the crest of the other wave, or trough of one wave meets the trough of the other wave. Therefore, the waves are in phase with each other, and therefore the displacement is maximum, and these points appear bright as a result of this constructive interference. So, these are the points where we have constructive and destructive interference. So, on your screen, the intensity of light will be alternative maximum and minimum stress. That's because of constructive and destructive interference. And we have these bright and dark bands, which are referred as interference fringes.